Right, so one thing I forgot to mention about section 1.2 is this idea of linear combination. In fact, we can say a vector is a mathematical object with which we can form linear combinations. So let's look at what a linear combination is. In general, the formula will look something like this. You may see something like this: CV plus DU plus, let's say, EW. Now this C, D, and E, these are constants, or we could call them scalars. They're real numbers. And this V, U, and W, these are vectors. Okay, so if I have vectors, I can form objects that are combinations like this. You can say they're sums of scalar multiples of vectors. So let's give an example. An example would be if I have a couple of vectors. Here, there's a vector here, 1, 3, 2, 2, minus 5, minus 7. Okay. So I have three vectors here. This is my V, this is my U, this is my W. I can multiply this one by a number, which is, let's say, 4. I can multiply this by another number, maybe minus 6. And then I can multiply this by another number, say 15. Okay. And I can add these together. Okay. And I can evaluate the result. Okay. And the way you evaluate the result, as I referred to last time, when you add vectors, you add the corresponding components. And when you multiply by a scalar, you multiply the corresponding components by that scalar. So the first component of this vector here, well, let's do it step by step that way. I can do this multiplication here, that will give me 412. I can do this multiplication here, that's going to give me minus 12, minus 12. I can do this multiplication here, that's going to give me what? I think that's 75, is that right? Yes, I think so, minus 75. And then this one would be, I think, minus 105. You can check that, maybe I got that wrong. All right. Then when you add these together, you're going to add the corresponding components. So the first component is going to be 4 minus 12 minus 75. And the second component is going to be 12 minus 12 minus 105. And whatever that works out to be, that looks like, it's going to be minus 8 minus 75, that looks like minus 83. Again, I'm doing this quickly, so I might have made a mistake, but the 0 minus 105, and that's minus 105. Okay, so this is the result of the linear combination. Now I can do this with 2 vectors, 3 vectors. I can do it with polynomials. I can do it with any type of vector. I can form this kind of combination, which is called a linear combination. And we're going to see this pattern very often in subsequent discussions. All right, so let me go back to my outline. So I mentioned that linear algebra is the study of vectors and linear functions. We talked about vectors, what they are. Let's talk about linear functions, what they are. Okay. The linear functions can be understood with reference to the figure on page 17. So let's go to the figure on page 17, which I've reproduced down here. We can jump to the PDF and see that. So we're in 15, so we're almost there. Oh, by the way, if you see these pictures, these are pictures of functions. You may have seen this idea of a function as a black box with inputs and outputs. Here's a simple function with one input and one output. You input x, you output 10x. Here's a more complicated function where you input 3 numbers, which you may recognize as a 3 vector, and I output 3 numbers, which is another 3 vector. In this case, you have an input that's a function, p, or a polynomial, maybe 5x plus 7, 5x squared plus 7x plus 3, I could input that polynomial, and I could output 2 different definite integrals. Now this is also a vector. This is actually a 2 vector. But this is a function that takes the input polynomials and output, which is a 2 vector. Okay, and in this case, the input for the function are functions themselves. You can have inputs of any type, of any mathematical type. And you can have a function of functions, but we won't go there. Right? Now, what's a linear function? So here's this picture that I reproduced also, that here we have a bubble diagram where you have the inputs here, and these inputs are in this bubble, which is called the domain. The domain is the set of possible inputs. And then here you have the outputs, and this is called the codomain, which is the set of possible outputs. Now, there's no real reason why the output bubble is bigger than the input bubble. He just happened to do that, I think, for just to make the picture more clear, because you got more stuff over here. Now, the function here in this picture is called L. So L is a function, also called a transformation or an operator. Those names are fairly interchangeable. But this L is your black box. This L takes the elements of the domain and produces elements of the codomain. All right? So in this case, it takes CU, and the output is L of CU. That's the notation. Whenever you have any input, in this case U plus V, you write the output as L of U plus V. All right, so here's a picture. So far, if I just focus on this part, this is a picture that's generally valid for any function. All right? Now, what's special about linear is the special form of L of CU and L of U plus V. I should make clear that the C here is a scalar. It's a real number. The U is a vector. It could be a column vector or a polynomial. But the C is a number, like 7 for square root of pi. All right? So L of CU for a linear function must be equal to C times L of U. They must be the same. All right. So here you see that vectors are objects that can be scalar multiplied, and linear function is a function that acts in a special way on scalar multiples. If I have scalar multiple of a vector, then I can hold off taking the scalar multiple. I can find the function first and then multiply by the scalar multiple afterwards. Right? Basically, you can say I can pull the C out of the expression. All right. Now, also, we know that vectors are objects that can be added. So here we have U plus V. A linear function is a function that acts in this special way on sums of vectors. L of U plus V is L of U plus L of V. In other words, I can add first and then take the function, or I can take the function first and then add. Right? So these two properties are called additivity and homogeneity. So when he says it doesn't matter if you add U and V first and then put it into L, or you can put into L first and then add. Okay, same thing with scalar multiple. Doesn't matter if you scalar multiply first and put it into the function, or you can put it into the function first and then scalar multiply. All right. All right. So here he makes the point that linear function, linear map, linear operator, linear homomorphism, linear transformation, they all refer to the same thing. Okay. Let's see. Now let me clarify something here. You have talked before, I'm sure, about lines. So if you can think of a line, you have an equation y equals mx plus b, where m is the slope, b is the intercept. I can think of my x as an input and my y as an output. Okay, so since this is an equation of a line, you might think this is a linear function. But in fact, a line does not represent a linear function. Okay, that seems a little bit strange, but the two meanings of linear are a little bit different. Here, this is a geometrical meaning, and this linear function is more algebraic meaning. There's some relation between the two, but they're not identical. For example, let's just give an example. Let's just take a very simple example that y equals x plus 1. Okay, so if I put it in, so my input is x, my output is x plus 1, right? And I can put a black box here, I suppose, and that's my L, right? So if my input is 1, then my output is going to be 2. If my input is 2, my output is going to be 3, right? Now, if the function were linear, then if I put in 2 times 1, then here my output should be 2 times 2, because I'm taking 2 times this value. My output should be 2 times this value if the function was linear. But in fact, you can see that that's not the case. So this does not work. So the function is not linear. It's not a linear function. Even though its equation of a line is not a linear function. Now we can fix this if I just take a function something like, here's example 2. If I take a function y equals 5x, you can check that this function is linear. In fact, all you need to do in this case, if I have y equals mx, and my b is 0, so it gives a linear function. Okay. So if you think about what this means graphically, this type of function, y equals mx, it can be graphed, is a line through the origin. Okay. So the graph of a linear function and this is a linear function on one vectors, is always a line through the origin. All right. So that kind of gives you an idea the relationship between linear and lines. Not all lines represent linear functions, but lines through the origin represent linear functions. Now here's an example of a linear function that you wouldn't think of. The derivative operator is linear. Right? Derivative operator acts on functions. It acts on functions that have derivatives, or we call them differentiable functions. And you can verify that the derivative of any number times a function is that number times the derivative. And the derivative of the sum of two functions is the sum of the two derivatives. For instance, if we go here and we want to take the derivative, just a little calculus review. Okay. Let's just do this. So the d dx is linear. Okay. You can give an example. If I take d dx of, let's say I take 7 e to the x, well, what's the derivative of that? Well, you probably know that you can take the 7 outside of the derivative, so this is just going to be equal to, and in fact it's just equal to 7 e to the x. And that's the same thing as 7 times the derivative of e to the x. Okay, so we see the 7 here inside, the 7 here outside. This operation, this function, this derivative, which acts on functions, is a linear operation. We can also say the derivative is a linear function. All right. On the other hand, if we have derivative of the sum of two functions, suppose I take x squared plus sine x. Right. Now, you know from calculus that to find derivative of this, you just take the derivative of x squared plus the derivative of sine x. And that's just expressing the fact that derivative is linear. Okay? So, just to finish off here, that we can write this linear property in general by saying that a linear function acting on linear combinations is the linear combination of the linear function acting on the vectors. Okay, so I mentioned linear combination at the beginning of this video. Here you can see how linear functions act on linear combinations. You can basically take out the constants. It looks like the distributive law. So you're kind of distributing the function in to the vectors, right? So that's it for this section.